With this presentation, we'll be covering book chapters 20, 21, and 23. The subject we're going to be covering, totally new subject, very different than anything else we talked about prior to this, and that is computer networking and how we connect computers together. We'll start off our networking discussion talking about some basic terminology that is used with networks. And of course, the first would be, what is a network? Computer networks are a group of computers that are in some way connected together so that they can share resources. Resources such as printers, internet connections, software, data, and so on. Bandwidth, the next term, refers to the amount of data that can flow through a network. And our general goal today is to increase bandwidth with our networks so that more data can flow, especially when you consider the fact that people are now using the internet, for example, for video streaming and so on, which requires a huge amount of data to flow and therefore very high bandwidth. Types of networks, we go over three here: LANs, WANs, and MANs. LAN stands for local area network, and it is a network of a group of computers connected together in a specific geographic place. It could be a building, an office, a home, a campus. All right, but again, all the computers connected together in the specific geographic location. Local area network. WAN means wide area network, and the difference is WANs cover large geographic areas. WANs can be huge. The best example of a WAN is the internet, and the internet covers the entire world. So that's how big that particular wide area network is. It even extends out to the space station. So WANs are really unlimited as far as how big they can be. The difference between LANs and WANs, to kind of summarize it here at the beginning, although we'll go in more details later, is the actual hardware used. LANs tend to be higher bandwidth over shorter distances than WANs. And the actual hardware used in the two different types of networks is very different. The third, a MAN, Metropolitan Area Network. These are an attempt to expand the geographic reach of LAN technology. Because I just mentioned, LAN technology is very high bandwidth, but restricted geographically. So with MANs, they're trying to expand that geographic reach to make local area network or very high bandwidth networks more widely available. Currently, there aren't a huge number of MANs, and where they do exist, they tend to be used by the government, police agencies, fire, and so on. Next, how do networks work in general? The data on a network is carried in little small segments or chunks called packets. So if you have a big file that you want to send through a network, let's say, for example, you are attaching a photograph to an email to send it to a friend. What your computer will do is take that large photograph file and break it into a bunch of little pieces into the packets. Each packet has the data it's carrying, the address of the computer it's going to, and the address of the sending computer. Best way, compare it to like sending something through the regular mail, and where you put it in an envelope. The envelope would represent the packet, and on the outside of the envelope you have to put the address of where it's going and the return address. Well, computer packets are kind of like that. Our discussion of networks in this presentation is going to be really broken into two parts generally. We're going to start out talking mainly about local area networks, and then after we've covered local area networks, we're going to transition into wide area networks. So the next few slides deal with local area networks. Now the first thing we're going to talk about is physically, how do you set up a local area network? And when we talk about physical setup, you know, how you run the wires and what hardware is involved and so on, you're talking about it, the term is topology. Topology refers to the physical setup or the physical design of a network. And through the years, there's been three topologies: bus, ring, and star networks. However, bus networks and ring networks are very rare today. They were an older technology that has fallen into more disuse. 99.9% of local area networks today follow what we call the star topology. So let's look at those specifically. How does a star topology network, what does it look like? And that's what we see in the diagram on the right. Basically, a star topology has an electronic device in the center, and each resource or computing device then connects directly to that central device. So we can see in the picture we have the little gizmo in the center, and we're going to talk more about those in a few minutes. But then we have a wire running from each computer to that central device, and we also have a network printer with a wire running from the printer to that central device. Now, why have star networks taken over? Why are they the most popular today by far? Well, first off, they're very inexpensive to install. The most difficult part of setting up a star network is physically running the wires. Although today, in many cases, and we'll talk more about this in a few minutes also, but star networks can also be wireless, which means you don't have to run the wires. But again, a typical star network, wired network, you have to run the wires that are going to be between the computer and that central electronic device. If everything's in one room, that's pretty simple. You just run the wires. If it's an entire building, then you're going to have to figure out how to run the wires through the ceilings, and that running the wires becomes the big part of it. Once the wires are installed, actually connecting up the computers and that central device is pretty easy. Next reason they're popular says one node fails, others not affected. What does that mean? Each computer in that diagram represents what we call a node, one section of the star network. Well, what it's saying there, if something goes wrong with one of those, in other words, if a wire is broken or a computer crashes or a wire becomes unplugged or whatever, the rest of the network goes on normally, and the only thing affected is the computing device, computer or whatever, on that one wire, that one node. Very different than, for example, bus networks and ring networks, where if one node fails, the entire network goes down. I used to teach a class, a lab, computer lab, and the computers were connected with a bus network. And every once in a while, one of the connectors would come loose in the bus network, and all of a sudden, no one in the room had connection to the network. Everything stopped working. So I would have to run around and figure out where it disconnected and fix it right then and there. Now, if the hub fails, and that hub we're referring to here is this electronic device in the center, which may or may not be a hub. We'll talk again more about that in a few minutes. But if the device in the center fails, the entire network is not available. The individual computers will still work, but you will not be able to use the network. That's the only way that the entire network would crash. However, the hubs, or those devices in the center, have become quite reliable, so that doesn't happen very often. And as I mentioned earlier, it is easy to install these networks. The last slide, we were talking about local area networks from the point of view of the topology, which is really the hardware aspects of it. Also want to quickly mention here the software side of local area networks. And luckily, we've already learned this in a previous chapter, so this is really a review. Basically, local area networks can be set up one of two ways. The client-server setup, or what we called a couple chapters ago, the domain. This is where there's one computer that controls everything about the network. It's a very centralized networking system. The other is a peer-to-peer network, or what we called a couple chapters ago, a work group. And this is where each computer on the network uses the network as a resource, but no one computer has more power than any other computer. It is not centrally controlled. Each computer controls itself. And the work group is usually a smaller, easier to administer. Client servers are larger networks, and usually you need someone with some professional training in order to actually administer the domain controller, or what we also call the server computer. Again, we talked about the issues of both of these. We talked about the domains and the work groups before. So this slide generally is review. Getting back now to the hardware aspects of local area networks, the next thing we're going into here is the hardware protocols. Now, first thing I want to talk about is the term protocol. So what is, in general, a protocol? It's a series of rules or procedures that are followed to complete a task. And you can have, there's protocols that, the United States culture, when we think about what's normal in our culture, it's a set of protocols. In the United States, typically the protocol is most everybody speaks English and so on. If you would go to another country, you might find the protocols very different. Language can be different. The way people act can be different, and so on. So again, protocols, that's protocols in a very broad sense. With computer networks, we're going to start out with hardware protocols. And protocols is one of the big subjects in networking. There's all kinds of different protocols. We'll probably be, by the end of this particular presentation, we'll have covered 4 or 5 different protocols, talked about what they are. But the hardware protocol is the first one, because that's what we're discussing, local area network hardware. Hardware protocols that is most common today is a protocol called Ethernet. I know a lot of you have probably already heard of Ethernet and said, well, what is Ethernet? Ethernet is a type of network. It's a set of protocols that control how all the hardware in a local area network works together. So for example, the wiring of a local area network, the actual wiring has to follow the Ethernet standards or protocols. The central electronic device I've mentioned a couple times. Again, that has to follow the Ethernet hardware protocols. The circuitry in the computer has to follow the Ethernet protocols. If everything follows the Ethernet protocols, it will all work seamlessly together without even worrying about what company or brand name the hardware is. So for example, you can buy wiring from one company, you could buy a hub from another company like Linksys or something. Your computers could come from Dell and Apple and whatever other companies, and because the networking hardware in them follows the Ethernet protocol, they will all work together. So now let's talk about some of the specifics of the Ethernet protocol. And the first thing we're going to discuss is the wiring. Now in this chart here, it shows 4 different types of wiring for Ethernet. The first two, 10-base-2 thin-net, 10-base-5 thick-net, those two standards generally are no longer used. They were really standards for a bus network or ring networks, and so we're not going to worry about those. The last two, however, are the ones I do want to talk about, starting with 10-base-T or also 100-base-T. This standard is also called, you hear it referred to as twisted pair wiring. And the reason for that is that the actual wires are made up of 4 pairs of wire that are twisted together. The reason they have to be twisted together is that by twisting the wires, it reduces interference between the wires. And what the real enemy of local area network systems is if one wire interferes with another wire. All wiring, any wire carrying electricity produces, and we've talked about this earlier in the semester, but produces electromagnetic interference. Electromagnetic interference can really mess up a 10-base-T or 100-base-T network. And so to eliminate, one way to eliminate the electromagnetic interference is to twist the pairs of wires together. And just by that, physically having the wires that way will eliminate the interference. Also, the interference in this case is, they call it crosstalk between wires. Twisting gets rid of the crosstalk. You won't actually see the twisting when you see a cable, an Ethernet cable like this, because the twisting is all done inside the cable. Now, a little bit more about this. What is the speed, the bandwidth of these systems? In this chart it says 10-base-T runs at 10 megabits per second, 10 million bits per second. That's standards not common anymore. The most common today is the 100-base-T, which means it's 100 billion bits per second. Much faster, 10 times faster than 10-base-T. And they even now have wiring standards that can carry data even faster than that, gigabits per second. But again, probably the most common today is 100 megabits per second as the speed. The cabling is what we call UTP or STP. The key thing there, the TP stands for twisted pair. And you can have two unshielded twisted pair or shielded twisted pair. Shielded twisted pair has extra shielding to eliminate external magnetic interference. Most times you don't need that. So unshielded or UTP is by far the most common cabling. On the end of the cables it uses the RJ45 connector, which it shows you that in the next picture to the right, what the RJ45 connector looks like. You've probably seen these. They're kind of like a phone connector but bigger. Now the last column is interesting. Remember, Ethernet is a local area network, restricted geographically. And now we see why. From the back of the computer to the central electronic device in a star topology Ethernet network, the maximum amount of wire is 328 feet or 100 meters. If the wire run is longer than that, the network will start becoming unreliable. And the longer it goes over those limits, the more unreliable it becomes, till where it's pretty much useless. So again, you are limited to 328 feet from the back of the computer to that central electronic device. Clearly a geographic restriction. You have to basically use this type of wiring is good to use within a building. You would not use this type of wiring if you're trying to connect, like a campus together with multiple buildings. The distance restriction is too small to effectively do that. But again, within buildings, the 100 base T is by far the most common type of wiring for an Ethernet network. Now the last line down here, where it's 10 base F, 110 base FL, all the way up to 1,000 base FX, these do not use conventional wires. They use fiber optic cable. Now, first off, what is fiber optic cable? It is strands of glass. Electricity does not flow through a fiber optic cable. Strands of glass carry light through the cable. And by turning the light on and off at one end, the light carried through the cable blinks on or off, representing on bits and off bits, and a light sensor at the other end then picks up the data. No electricity actually flows through the cable. And one other thing, a fiber optic cable only works in one direction. So you need to see, when you're dealing with fiber optics, you always see the cables in pairs, twos, so that one cable carries in one direction, the other one carries the data back in the other direction. The advantage of fiber optics is that it doesn't carry electricity, so electromagnetic interference and things like that do not affect the operation of fiber optic. It's in operation, it's pretty much impervious to any interference. You don't have to worry about electrical spikes or surges or things like that, lightning storms damaging your cables, whatever, because again, no electricity involved with the cabling itself. Now, the cabling works up to, I should rephrase this, in the local area network standards for fiber optics, which is what we're looking at here, the cabling can be up to 2 kilometers or 6,562 feet from the back of one computer or device to the back of another device, which clearly gives you space or enough cabling to run between buildings. So, for example, using the SUNY Oneonta campus, it uses 100 base T wiring within the buildings, and that connects to fiber optic cabling, or what we call the fiber optic backbone, that connects all the buildings together. And again, we're talking about Ethernet here, local area networks. There are other types of fiber optics that are used in wide area networks, where the distance the signal is transmitted can be much greater than 2 kilometers. You can have a fiber optic cable that's hundreds of miles long, connecting cities together. But again, those are different standards, and they aren't the ones used in local area networks. They are the systems used in wide area networks. Actually, kind of as a side note here, fiber optics has had a huge impact on the way we do things. If you have to think about this question, how much would you use the internet if it cost you $20 an hour to be connected to the internet or to use it? Well, usage would drop off dramatically, $20 an hour. That's the way it used to be to use networks. There was an hourly charge. Well, as fiber optics moved in and the technology for communications with fiber optics improved, the cost of providing long-distance communication dropped dramatically. And that's what really allows us today to basically have almost free communications. I mean, today if you're home, you want to use the internet, you need to have a subscription with an internet service provider. We'll talk more about that later. But this subscription basically gives you unlimited access to the internet as much as you want. There's no hourly charge or anything like that anymore. Also has had an effect on phone services. That's why you can use cell phones so inexpensively today, because the fiber optic systems we have make the actual transmission of the data so cheap. This slide here just shows you the different kinds of wiring that are commonly used in networks. And the one in the upper left-hand corner, upper unshielded twisted pair UTP wiring, where you can see there are pairs of wires inside the cable that are twisted together. And again, the reason they have to be twisted is to reduce electromagnetic interference or crosstalk. Directly below that, we also have the shielded twisted pair. Not as common. Basically, has the twisted pair wire, and then surrounding that is a foil, aluminum kind of a metal foil layer that provides additional protection to reduce interference. Upper right-hand corner, coaxial cable. That is the type of wiring that comes into your house through the cable TV system, and it can be used, and we do use it for the getting access to the internet and so on through your cable system. Again, we'll talk more about how that works in a little while. And then below that, we have two examples of fiber optic. And at first, when you look at these, you say, well, the fiber optic looks like the coaxial cable. Well, it only does in these pictures. The coaxial cable, the little wire in the center, is actually a copper wire. It's wiring, carries electricity. With the fiber optic, the little wire in the center is not a wire. Again, as I mentioned a few minutes ago, it's a strand of glass, and it carries light. Now we're going to take a look at the other Ethernet hardware device that you need to set up the network, and that is the electronic device that goes in the center of the star. Actually, we're going to look at all the hardware, the rest of the hardware devices, beyond just the cabling. The first thing I do want to mention is what's called the NIC, the Network Interface Card. This is the circuitry that's in the computer that connects to the Ethernet network. It's called a network interface card, even though on most computers today the circuitry is built into the motherboard. But when networking was new, computers didn't come with built into the motherboard circuitry. So you would buy literally an expansion card that was your network interface card that gave you then the port to connect to Ethernet. Again, today, almost all, 99.99% of computers come with the network interface card circuitry built into the motherboard. And again, it's Ethernet, so therefore it follows that standard, so that all the different brands of computers will work the same. Now going on to the devices in the center of a star. The first device was called the hub. And the hub basically brought all the wires from the different nodes, the computers, together in one place so that they all could talk to each other. The hub was a very simple device. It simply received data from a node and rebroadcasted all that data to every other node or every other computer connected to it. It was a broadcast device. And that's what the diagram is showing here. Computer A sends some packets to the hub. The hub then, you can see, is sending those same packets to computer B and C and to the bridge, which we'll talk about in a second. So the hub the problem with the hub is that only one computer at a time could be sending packets. All other computers connected to the hub then would be in receive mode to receive packets. If two computers wanted to broadcast or send packets at the same time, whichever computer got their packets to the hub first is the one that got to broadcast the packets, and the other computer would have to wait until the first one was finished. Now, if you didn't have very many computers on the hub, 5, 10 computers, this was not a big deal. But the more computers added to the network, the more problems this created, and we started to see more and more of a problem called data collisions. A data collision is when two or more computers want to transmit data over a particular channel or wire at the same time. Only one computer can use it at a time. If you have more than one computer trying to use it, they're colliding. The second computer to get there, the first computer to get there gets to do it. The second computer and all those after have to wait till the first computer is done. So hubs, although were simple, were reliable, they really limited the data throughput on a network. Now, next they came out with a bridge. And the idea of a bridge is that it didn't simply broadcast all the packets. It kind of sorted through them and only passed the packets on that were headed to computers on another network segment. And you can see this in the diagram. From the bridge, it breaks into 3 different network segments. Each one of those segments would have its own hub and its own group of computers. So the bridge was a way to connect different star networks, small star networks together, creating a bigger star network. And this could work, for example, you'd have a hub in a building, and all the computers in that building would connect to the hub. Then you have another building, you put a hub in the second building, and all the computers would connect to that hub. And then you'd run a line between the two, then you'd run a line between the two buildings, and that line would go through a bridge before it connected to the second building. And that way, the bridge allows you to kind of subdivide the network, and it allowed you to reduce the number of collisions that were in the network. Third thing mentioned here, a switch. A switch is the newest type of device and pretty much taken over from both hubs and bridges. A switch replaces a hub directly. And the big difference is a switch does not, when it receives packets, it does not simply broadcast them to everything else connected. A switch actually looks at the address of the packets and forwards the packets to the computer they're supposed to go to, and not to every computer. And therefore, if two other computers are communicating, another computer is sending packets at the same time, a switch can simultaneously handle that second flow of packets. So the big deal here is with a switch, the collisions, data collisions, are reduced tremendously, greatly improving the performance of a network. Now, let's add in another important part to this whole networking scheme with Ethernet and star networks, and that is wireless local area networks. Now, how does that work in? Well, basically, a wireless LAN is the same as a wired LAN. No difference, except with a wireless LAN, you do not have a wire between the computer and the network. Connected to the network, you have another device called a wireless access point. And then in the computer, you have to have a wireless network interface card. Many laptops today, and I'd mentioned this, I don't know, a couple of chapters ago, the fact that a lot of computers today have, a lot of laptops have two network interface cards in them. One for a wired network, one for a wireless network. That way the computer can work with either type of network. But again, the computer has the wireless card in it, and the network then has a wireless access point, and the computer then, using radio waves, connects to the Atlas access point, and now it's on the local area network. So again, works is pretty much the same, except you're eliminating the wire between the network and the computer. Now, one other thing I should mention, wireless access points work like a hub. Many times I get questions, well, how many computers can connect to one wireless access point? And the answer to that, number one, depends on the access point itself. Some access points do have limits, you know, like 15 or devices at one time or something like that. Other access points don't have those limits. But in either case, it works like a hub, which means that any packets coming from a computer using the access point or off the network using the access point are simply broadcasted to all other computers using that access point. And the rule still applies that only one computing device can broadcast at a time through the access point. So basically, the more computers using an access point, the more data collisions you're going to have, and the slower the network is going to become. Now, I should mention real quickly, some of the brand new access points that are coming out now do allow for more work more like a switch, and they do allow for simultaneous communications with different points. But the traditional ones, the ones that are generally in use today, work like a hub, and therefore more computers you have, the more collisions you're going to have. This slide goes over the what are called the 802.11 standards, which are the Ethernet standards for wireless communications within Ethernet. And so your computer and your wireless access point has to follow at least one of these standards. And basically what we see, if we look at the little table there, we have 802.11a. 802.11a was the first wireless standard. It was only worked up to between 25 and 75 feet, so it was really a very short range. It used a 5 gigahertz radio frequency, but it had a pretty good speed of 54 megabits per second. So it was fast, but it was very short range. Now, that was then replaced, or supplemented, I should say, by 802.11b. 802.11b would work up to 150 feet indoors and up to 300 feet outdoors. And again, depending on the building and obstacles and what's between the two objects that are talking to each other. Used a 2.4 gigahertz frequency and ran at 11 megabits per second. So 802.11b, much longer range, that was good, but much slower, that wasn't so good. Then 802.11g was introduced, and you notice distance-wise, range-wise, it's the same as B. Frequency is the same. The only thing different is the amount of data, the capacity, the speed. Instead of 11 megabits per second, it's 54 megabits per second, much faster. And one other thing about 802.11b and 802.11g, they're compatible with each other. So if you have a computer with an 802.11b network interface card in it, it will be able to connect to a network, wireless network, where the access point is 802.11g. They will work together, but they'll just work at the slower speed. A few years later, 802.11n came out, and again, N was like B and G, compatible with each other. Same 2.4 gigahertz radio waves, same range. Big difference again, the speed, capacity, 600 megabits per second. So you can see that's a little less than 12 times faster than 802.11g. So 802.11n was a big jump in the speed of wireless communications. 802.11n has been replaced. Well, not replaced. You can still buy 802.11n networks. It's still quite common. But they do have a newer standard. I forget what it is, 802.11xl or something, I forget. That's faster still. And that's the standard that it does get away from the hub concept I was talking about in the last slide, where it's more like it operates like a switch rather than a hub. Where 802.11a, b, g, and n all work like a hub. One other thing you run into, which I should mention, you'll see there those central devices to set up wireless communications, which we call routers. You'll see now they're selling what they call dual band routers. And what does that mean? That means that the device, the wireless access point, is actually creating two wireless networks. One of them will be, for example, 802.11n, perhaps, or the newer standard, and the other one will be 802.11a. So it builds the 802.11a standard on top of, or simultaneously with 802.11n or whatever. And if your device, your computer, or your cell phone or whatever, understands both bands, you get to choose which one you use. So if you're in a situation where at home where you have mother, father, brothers, sisters, everybody's using the computer, and things are getting slow, if it's a dual band router, you could go in with your computer and connect to the 802.11a band, and you'd be the only one on it, and therefore your communications would be much faster than everyone else's using the same wireless network. But again, both the central device, the wireless device, router, whatever you want to call it, and the computing device, computer, cell phone, whatever, has to understand the 802.11a standard in order to do that. And of course, the downside of 802.11a is the range is much shorter. Earlier in this presentation, I mentioned protocols. I said we'd learn lots of more about protocols. First one we went over was the Ethernet protocol, which again is the hardware protocol for local area networks. Well, now we're going to look at some of these software protocols. And the next one we're going to look at is actually two protocols that work together, TCP/IP. This is the protocol that actually moves the packets through a network, that actually controls how the addressing works on the packets to get the packets to the destination computer. TCP stands for Transmission Control Protocol. IP stands for Internet Protocol. They are two separate protocols that work together. The TCP is the protocol that formats the data packets themselves, the data packets that carry the data. The IP, the Internet Protocol, then formats the addressing system so that the packets have an address to direct them to their destination computer. TCP originally was a wide area net, actually both of them, TCP/IP I should say, was originally a wide area network protocol, but it worked so well as the internet came in that they've expanded it to also work on local area networks. So at this point, where I said we were talking about local area networks and we talk about wide area networks, well, with this discussion, we're actually starting the switch over and talking about how wide area networks work by discussing these protocols. So again, TCP is the packet protocol, IP is the address protocol. Next slide, again, we're continuing to talk about the addressing systems on a computer. Now, we just talked about TCP/IP, and I mentioned that the IP was a protocol of internet addressing. So we'll see that again here as part of the addressing system. Actually, with computer networking addresses, there are 4 different parts that we have to deal with. First is what's called the MAC address, Media Access Control Address. Also, some people call this the hardware address. The reason is that it's built into your network interface cards, and it's a permanent address attached to those network interface cards. It never changes. The MAC address is placed in the network interface circuitry when those circuits are manufactured. When you buy the computer, you get the MAC addresses in those circuits. Again, they never change. Mainly MAC addresses are used on the local area network side of things, not so much the wide area network, because again, some people also call these the Ethernet address because it is part of the Ethernet system. Next point down, IP address, 32-bit address, blah, 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 blah. This is the address of the internet, the addressing system of the internet. This address does not come with your computer. You receive an IP address the first time you connect to a particular network. So, last fall, when you came on campus with your computer for the first time, you connected your computer to the campus network. At that point, you were assigned an IP address to your computer. Then you went down to your apartment and you set up a local area wireless network down there. And the first time you connected to that with your computer, that network assigned you a different IP address. You go to McDonald's and you use their network while you're having a hamburger. You get an IP address from the McDonald's network. Now, how long do you keep those IP addresses? Well, that depends on the network you connected to. The campus network, you'd probably keep that IP address for the entire academic year. Your little home network that you connect into, you'd probably keep that IP address forever. The network out of McDonald's, you might only keep that IP address for 12 hours or something like that before you lose what's called the lease on the address and it goes away. Now, IP addresses are a bunch of numbers, and people do not remember numbers well. So the third type of addressing system here, character-based names. These are computer addresses that use letters and words that have meaning to people. And we'll look at how that system works. What we're going to discover is the computers, networks themselves, don't understand character-based names, so they have to be converted to IP addresses. The fourth part of networking addresses, port numbers. We'll take a quick look at those. They're a little add-on to the IP address. All right, let's go back now and look at MAC address in a little more detail. As I mentioned, the MAC address is built into the hardware of your computer, and it's generally used by Ethernet parts of a network, in other words, the local area network. So what we see here are 2 local area networks that are connected by the internet. If two computers within one local area network want to talk to each other, they can simply address the packets using the MAC address. But if one computer in one of those local area networks wants to talk to another computer in a different local area network connected by the internet, then it has to use the IP address of the computer it's trying to talk to. So again, the MAC addresses are hardware addresses, local area network addresses. IP addresses are more the long distance addresses. But again, I did mention modern local area networks today do use the IP addressing right in with the MAC address within the local area network also, because IP has become such a universal addressing system. So now let's look at IP addresses. In this slide, the numbers down there, 207.46.249.29, are an example of an IP address. There are what's called octets and so on. I'm not going to get into all the details of how they work. But basically, the group of numbers on the far left tell you the region that the computer is in that you're trying to communicate with. And as we work, each grouping of numbers going to the right gives you more details until finally the number on the far right gives you the specific computer you're trying to talk to. The internet needs these numbers, these IP addresses, on the data packets in order to communicate. However, we as people don't usually know the IP addresses. As I mentioned a second ago, people don't remember numbers well. They remember words. So we use character-based names, and you can see an example there in the center of this slide, www.microsoft.com. That is the character-based address for the IP address shown here, 207.46.249.29. So we would type in www.microsoft.com, press enter. But by itself, that character-based address cannot direct the packets to the other computer. It needs to know the IP address. So there's one little step in between. We have something called DNS, Domain Name System. I remember previous presentation I mentioned the word domain can get a little confusing because there's more than one definition. Well, here we're seeing a different usage of that term domain. Domain here means the organizational that owns a particular set of computers. But anyway, the DNS, what happens, you type in www.microsoft.com, and when you press enter, that address is sent to the internet. But the device where you enter the internet says, well, I can't use that. So that device sends those characters to the DNS server. That is basically another computer with a big database showing you character-based names and their corresponding IP address. So you would send your message automatically to the DNS server. It would look up www.microsoft.com. It would discover that the IP address is 207.46.249.29. That bit of data would be sent back to your computer, and then the data packets you're trying to send would have that IP address. I should also mention the data packets would also have, if available, the MAC address of the computer you're sending it to, and it also has return address, the IP address of your computer, and definitely the MAC address of your computer is included in the data packets. So the computer you're sending to always knows where the message came from. But at any rate, after DNS server, you look up the IP address. The IP address is then placed into the packet, and the packet can then be sent through the internet to the other computer. Now, let's take a closer look at the character-based naming system that we use. In the last slide, I'd mentioned the www.microsoft.com. Well, how does that work exactly? That was an example of what we call a URL. That stands for Uniform Resource Locator. That is the character-based name system that we use with the internet. So basically, your computer sends the URL to the DNS domain name system. That looks up the corresponding IP address, which is then sent back to your computer to be placed on the packets. Now, URLs have a specific format. And down at the bottom here, we see a format of a URL. And in the center, we see course.com. The course.com is the domain. It represents something, a word that represents a specific organization on the internet. A company or a nonprofit or a family or one person or a school or whatever. All right, so in this example, course.com was a book publishing company. Here on campus, you have oneonta.edu. That's the domain name. Microsoft.com, example we used from the last slide. Ford.com. You know, all these are different domain names. How do you get a domain name? There are companies that sell them. So if you wanted a domain, if you wanted your own personal domain name, because you're going to plan to set up your own web page or something like that, you could buy your own personal domain name. They're not very expensive, probably different stores, different so on, different prices. But I would say for 3 years or so, a 3-year lease on a domain name would be $50 for the whole 3 years. There is one nonprofit organization that works worldwide to organize all the domain names, but you don't deal with them directly. As I said, to get a domain name, you go to one of the domain name retailers. You may have heard of GoDaddy.com and wondered, well, what the heck is the business? What do they do? One of their big parts of their business is selling domain names. So, domain name is owned by the organization. The www in front of it, World Wide Web is what www stands for. That refers to the specific computer you're trying to get to within the domain. So with course.com in this example, we're trying to get to the computer named www. Most companies, let's say all website companies or whatever, organizations with websites, have at least one computer named www, and that's the computer where their main web page resides. There are other things that can be used there instead of www, but what they would be would depend on the website you're using and so on, and how they've set up their computer system. If you only have one computer supporting your web services, then that one computer will be www. To the left of that, we have HTTP, Hypertext Protocol. Again, talking about protocols, the protocol of the URL addressing system is part of the Hypertext Protocol. It's a web protocol. To the right of the .com, we have /myfolder. That can be lots of different things depending on the website, but that refers to what folder, just like you have folders to store data files on your computer, you can have folders to store web pages on a web computer, and that refers to the folder that the web page is actually stored in. And you might have folders inside of folders, so it might be my folder / I don't know, picture folder slash Joe's pictures slash, folders inside of folders. The last part of the URL, way over on the right, is the file name. It says here my file, but that's the actual file name that contains the web page. All right, and that file has .html. It could be also .htm. They both mean the same thing. HTML refers to the hypertext markup language. It is a programming language of web pages. So if you wanted to create a web page, the way most of them are created is you get a programmer that knows HTML, and they create the web page using HTML. And again, the extension .html just tells the computer that's the type of file it is. And again, HTML is part of the hypertext protocol that covers the protocol of the internet. So again, these are examples. Now, typically when you're actually using these URLs, you don't have to type in the whole thing anymore. Back in the old days you did, but now you just type in, usually on a computer, the domain name, and it'll get you automatically to the home page of that organization, which would be on their www computer. Again, the way it works is you type in this example, course.com, it would go to the DNS server and return the IP address to your computer, which will then be placed on the packets and sent to the course.com computer. Oh, one other thing, I almost forgot. The .com, that indicates the type of organization. Com is for commercial. Other ones you might see there, of course, .edu, Oneana.edu, educational, org, usually is non-profit organization, BUS for business, MIL for military, GOV for government, and then if you're accessing sites outside the US, there'll be some extra letters surrounded by a period, 2 letters that are the country code that is kind of mixed in there also. The final part of addressing port numbers, basically the port numbers are added to the IP address by the sending computer, and the port number directs the data packet to specific software on the receiving computer. In this little example here, we see the network. There's a guy walking on the network with TCP on the back of his shirt. That's a data packet. He's carrying a data packet to the computer, which is represented by the brown box. And you can see the address, the IP address is 138.60.30.5. And if you see on the brown box, the IP address of that computer is that address, 138.60.30.5. But there are 2 different pieces of software that data could go to in the computer. There's the email service and the web service. Email service, notice, is port 25. Web service is port 80. If we look back at the address where it says this is for 138.60.30.5, we then see :80. The :80 is the port number, and you can see :80 will cause that packet of data to go, in this particular example, to the web server. So again, it directs the data to the appropriate software within the computer. 95% of the time, you don't have to worry about port numbers. They take care of themselves. Very rarely, and a lot of times it's with gaming. If you're doing online gaming, sometimes you might have to make manual adjustments to the port number. But for most of the time, they take care of themselves. All right, now that we've finished discussing the variations on computer addressing, let's try to pull this stuff together as far as wide area networking goes and talk about how a wide area network, such as the internet, actually works. And the key component, there's two parts to a wide area network. There is the communication links. Most of the time, those are fiber optic links running over great distances, but they might also possibly be a satellite link or some other things. So that's the wiring, the links that actually carry the data packets over great distances. And the other component of the internet are the routers. A router, it's a communications device that controls the flow of the data packets. And basically, it's a much more advanced device than a switch, which we talked about a little while ago. Because a router can actually look at an IP address and then direct that packet in the proper direction. And a router basically uses two rules when it's directing IP addresses. If it has a choice of two different communication channels or links, it will always direct the packets so it gets closer to the destination. That's rule number one. And rule number two, if it has a choice of links, it will choose the link that is less busy, so that it's always trying to balance the load between the different links. So no single link gets overloaded. So for example, in this little diagram, we have network A, some guy in Sydney, Australia, and he's got packets going from his computer to a web server in New York City. So the packets come out of his computer addressed with an IP address. The router looks at the IP address and has a choice. It could send it forward it to router 3, or it could forward it to router 2. Either one sends the packets in the correct direction. The question is which one? Well, it'll choose the communication link that is less busy. So if the connection to router 3 currently has lots of packets on it, it'll send these new packets through router 2. Router 2 doesn't have a choice. It'll just forward the packets in to router 4. Router 4 has a bunch of choices, and again, it would send them closer to the destination, and it would choose the link less busy. So again, what is the internet? A bunch of communication links and a bunch of routers. The next thing you might say is, well, what does a router look like? Well, that's an interesting question, because there's all kinds of routers. Routers can range anything from a large mainframe computer running Unix, costing millions of dollars, down to a little box that you bought for your house that costs you $80. Right? There's all kinds of different routers. Most routers out in the internet are actually computers running router software, and the software usually is Unix, the Unix operating system, because that directly supports the data communications that we're talking about here. So again, the internet is made up of a bunch of communication links and routers. Since we were just talking about routers, let's talk about a home router. These are the little boxes that you can buy to set up wireless within your own home, apartment, whatever. These little boxes, we call them routers. They cost between $50 and $200, depending on how fancy one you want. Where you buy them, you can buy them at Walmart or Best Buy, or you can buy them from Amazon or whatever. Now, we call them routers. They're actually much more than just a router. Basically, these home routers are everything you need to set up a local area network in one box, one electronic device. So what is in there? Well, a router is in there, and the router then routes the data packets coming from computers connected to this out to the internet, and receives data packets from the internet and routes the packets to the appropriate computer. Now, it does that using two different things. Switch. Most of these home routers on the back have the option where you can plug in computers with wires. And there's usually 4 to 6 ports there that allow you to plug a computer, 4 to 6 computers total in. These plugs are a switch, just like we talked about earlier, that device that goes in the center of a star network. So the switch circuitry is built in. And then, of course, the way most of us want to connect to this thing is wirelessly. So also in there is a wireless access point, 802.11 G or whatever, depending on how new it is and how much you spent on the thing. But again, it gives you wireless access point. All the same things we talked about a little while ago apply. Now, other things in there. You can connect wired to it. You can connect wirelessly to it. It connects to the internet. Another important thing in there is something called Dynamic Host Configuration Protocol, DHCP. A little while ago I mentioned where you get an IP address from is the first time you connect to a particular network. That network gives you your IP address. Well, that's what the purpose of DHCP is, to assign IP addresses to any computers connecting through this particular router. So you connect with you get a brand new computer, you're setting it up, you connect to this new router that you have for the first time. The router creates an IP address and assigns it to your new computer. And you'll probably keep that IP address for as long as you keep that particular router. They usually don't reassign them. Every different computer connecting to that router will be assigned a different IP address. Every different device, cell phone, printers, whatever, will be connected, will be assigned its own IP address by the DHCP in the router. That way the router knows how to direct the data packets when they come in off the internet to get them to the appropriate computer. Another thing built into the router is management software. Most people never actually see this, but you can change things about the way your router works by using this management software. It's usually you get access to it through a web browser and by typing in a very specific IP address that's given to you by the instructions that came with the router. You type this IP address in, it takes you into what looks like a remote web page, but it's actually a web page coming from the router. And it allows you to, it's a big menuing system that allows you to make all kinds of different changes to the way the router works. I do not recommend you try this out and change anything unless you really know what you're doing, because you can mess up your router if you make the wrong changes. Finally, the router provides what we call WPA2 security protocol. And this is a protocol to encrypt. Remember we talked about encryption a little bit in the last presentations. To encrypt the data flow between a wireless data flow between your computer and the router, so that the data flowing between those two things cannot be spied upon by another computer. And it also keeps other computers that are not supposed to be using the router from using it. For example, let's say you set up one of these routers in your apartment, and you have people living above you and on each side of you and below you in the apartment. Well, wireless is a radio signal. Do the walls of the apartment stop those radio signals? Excuse me. No, they don't. So the people above you and on each side of you are receiving your wireless signal from your router. If you don't use WPA2 security, they'll be able to use your router. So you're paying for the internet and they're using it for free. But by activating WPA2 security, every device that connects to the router has to be given the router password. So you use the router password to connect your computer, your cell phone, your roommate's computer, your roommate's cell phone, your printer, whatever. That gives your computing devices access to your router. The people in the other apartments do not know your router password, so now can they use your router to connect to the internet? No, they can't. So again, those home routers we buy are everything you need in one box to connect and set up a wireless or wired local area network in your own location. Next thing, you actually want to connect a computer to the internet in your own apartment or your home. What do you need? How do you do that? Well, first off, you must hire an internet service provider, ISP. ISPs are companies that sell internet services to individuals. Around here, typically if you live off campus, the most common ISP used around here is Spectrum Cable, which gives you cable TV, and they sell cable TV, they sell cable internet services. If you live on campus, your ISP is the college. They provide you with internet services. Different places, different companies will provide internet services. Now, the most common form of connection from a home to the internet is through cable systems, cable television systems, where a cable comes into your house from a cable outdoors and it connects to what we call a cable modem. All right? The cable modem takes the computer signal off the cable coming into your house and it converts it to an Ethernet signal, Ethernet networking system, which then, if you want, you can connect directly to a computer through the network interface card. If you're going to do wireless and you have a router, the cable modem wire would not go directly to a computer. The cable modem would then be connected to the router, and then from the router it would connect to the computer, either with a wire, another wire, or wirelessly. But again, so more typical today is cable service coming into the house, going to a cable modem to router, router to computer. Now, there are other ways of getting the internet besides cable. One way, which is actually losing in popularity today, but it is out there, is what we call DSL, Digital Service Line. That's a special digital line using regular phone wires. It does not have the speed that cable has, and that's one of the main reasons it's not as popular as it used to be. A third option, which is gaining in popularity, is fiber optic line coming into your house. For example, we don't have it around here in Oneonta, but if you get Fios from Verizon, that is, Fios is a fiber optic system coming into your house, and it would go to, instead of a cable modem, it would go to a fiber optic modem, and then the rest of the connections would be the same, router, computer. The advantage is fiber optics is the fastest communication system, so you're going to, with fiber optic systems like Fios, it's going to be a much faster system. Although you do pay different amounts depending on how fast you want it to be. The faster it is, of course, the more expensive it's going to be. But that's how you connect to the internet. Now, with an internet, modern internet connections, where you're always connected to the internet whenever the computer is turned on, you start worrying about computer security. And the last presentation, the next one we do, covers a lot more about computer security as far as the viruses and so on, how to protect your computer from all those types of things. But we're going to start that discussion here talking about a firewall. Whenever you have a computer that is connected to the internet all the time, it should be protected by a firewall. Now, what is that exactly? Well, it's a way of, the purpose of firewalls are to keep computer intruders, or also what we call hackers, from coming into your computer and looking around and doing things with your computer without your knowledge. The firewall, what it basically does is stops computer intruders. Now, there are three forms of firewalls. There is firewalls that are built into your operating system. There is hardware firewalls and software firewalls. And so let's look at firewalls built into your operating system first, because that's the firewall that most people are actually going to use. For example, both the Windows and the Mac operating system come with a built-in firewall. Now, these firewalls that are built in are the simplest forms of firewalls. What they do is they put your computer into what's called stealth mode. What that means is it makes your computer invisible to intruders from the internet. The way it does is by telling your computer, it's a very simple system, it tells your computer not to respond to the ping command. P-I-N-G, the ping command. What is that? That is a network command that network technicians use to test networks. And for example, let's say your internet connection is not working right. So you call up your customer support from your internet service provider and you say, you know, things are really slow here. And so the customer support person will ping your computer. And then they will be, the answer will be sent to them, and it'll show how much time it took for the ping to get to your computer and for your computer to respond, and then for the ping to get back to their computer. And they can tell by looking at those numbers if the network is working properly or not, or if it's very slow. So again, that's the purpose of the ping command. The problem is that hackers use the ping command to hack thousands of computers all at once with different IP addresses. And then when the computers respond, the hacker or intruder now knows that that IP address is an IP address to a computer, that they could then use that IP address to break into the computer. But what these operating system firewalls do is they cause your computer simply to not respond to the ping command. So the hackers ping a bunch of computers, including yours, and instead of sending the message back, it stays silent. And so the hackers think, well, there's no computer at that IP address, therefore, I'm not going to use it. So again, it makes your computer invisible on the network to hackers. Now, let's look at, that's, as I said, the operating system firewall. Let's just look at that in a little more detail in the next slide. On this slide, we see what the Windows firewall looks like if you go into your computer settings, the security settings, and you look up how the computer security is set up on your computer. You can actually see the Windows firewall screen, which is what we see here. And you can see down in the center it says Windows firewall state on, which means it's turned on. Basically, the only thing you can do with a Windows firewall is turn it on or off. There's some other little things, but they're not that important. The main thing is turn it on or off. by default, the operating system firewalls are turned on because there's really no reason to not use them unless you're having problems and the internet service provider needs to ping your computer to test it. At that point, you could turn the firewall off by going to the screen, clicking where it says on, and get the choice for off. Then when the internet service provider is finished testing and doing what they do, you would come back to the Windows firewall or the Mac firewall and turn it back on. So under normal circumstances, it should always be on. And the nice thing is it's simple to use. It's on normally anyway. It comes with your computer, so it's free. Another type of firewall that you can get is what's called a hardware firewall. This is where you have a piece of hardware that isolates the computers of a network from the internet. In this diagram, we see how that would work. You have the internet, and then you have your cable modem that you've obtained from your cable company. Then you get the hardware firewall, and then the various computers all connect to the hardware firewall. Now you think, well, the computers come with the firewall for free. Why would I go out and buy this extra piece of hardware? Well, chances are you may have already purchased it, because one of the other functions of a home router that I was talking about a few minutes ago is they are also a hardware firewall. Hackers trying to break to your computer might be able to ping and get to the router, but remember, the router assigns all different IP addresses to each computer connected to it. So the hackers can't go through the hardware firewall to find out what those IP addresses are. So just by the very design and the nature of how routers work, they stop hackers, can stop most hacking. And like I said, if you've got a home wireless system set up with a home router, it's there already. So that's another layer of protection. And again, you'd still leave your firewall turned on within your computer to give you that layer. So there now you've got two layers of protection against hackers. The third variation on firewalls is to actually purchase an actual piece of software to load on your computer that is firewall software. And in this slide I've shown you an example of a piece of software called Zone Alarm. This is a firewall package, and it's considerably more sophisticated than the other forms of firewall that we've talked about. It does a lot more. I've chosen Zone Alarm because you can actually get this piece of software for free. There's a free version, and then there's a fancier version that you can buy. Now, what does Zone Alarm do? Well, number one, it sets up a basic firewall, which is the same as your operating system firewall. It puts your computer into stealth mode. So if you had Zone Alarm, you would turn off the operating system firewall and then turn your firewall, the basic firewall, on in Zone Alarm. And you'd have the same thing. Your computer would not respond to ping commands. But the other thing, as I mentioned, this does more than that, because Zone Alarm, or these types of software packages, also watch outgoing data leaving your computer and want to know if it's okay to send the data out. So what will happen is when you first install this, it's kind of a pain for the first couple of weeks, because when you first install Zone Alarm, the first time a particular piece of software wants to send data out of your computer, you'll get a message, is it okay if this program sends data out? Yes or no? You say yes, the software will remember that that software is okay to send data out, so it'll never ask you that question about that piece of software again. If you say no, Zone Alarm blocks that data from leaving your computer and will then block that data forever until you change the setting back again. So that piece of software will be blocked from sending data out. The idea is if you get some sort of virus or some spyware software that's trying to send data out of your computer, that the Zone Alarm will block that data from leaving your computer. The problem is when you first set it up, you're constantly, every time you use a different piece of software, it's going to ask you, is it okay if this sends data out? And you've got to decide, is it okay or not? And sometimes the name of the software that is listed in Zone Alarm isn't necessarily the name of software that you're familiar with, because they use different file names within software and so on. So for the first few weeks you're bombarded with these questions, and you can't just say yes to everything, because that means you're defeating the purpose of the Zone Alarm software. And you can't say no to everything, because that's going to block stuff that you want to work. So you really, every time you get one of those questions, you have to stop and think about it. Yes, do I want this software to do it? Or no, don't I want this software to do it? And it'll give you guidelines, different pieces of software and so on. So there is some help features there available. But again, for the first week or two that you own it, it constantly is doing that. Once you've got it set up and it's gone through that procedure, then it pretty much sits in the background, does its work, and protects you. So it works really well. One other interesting thing that you can do with it, it actually will track how many hackers try to break into your computer and give you their IP addresses. So in a sense, you could actually use Zone Alarm to turn the tables, and even though they never got your IP address because you were in stealth mode, you now have the hacker's IP address. What's scary though is how often a computer will try to hack into your computer. Basically, with a brand new computer that you've just set up, someone will try to hack into it within the first 4 hours of it being online. That's how long it takes them to discover. So these firewalls are very important for your security. All right, that completes this presentation. And I said we have one more presentation, and this last presentation really continues with the security questions and so on that we've just started here.